PARP
inhibitors and Parkinson's disease. Hey everyone! Welcome back to our channel. Today, we're diving into a fascinating topic that combines cutting-edge research with real-world implications: PARP inhibitors and their potential role in treating Parkinson's disease. So, grab a comfy seat, and let's get started. First off, let's talk about Parkinson's disease itself. Parkinson's is a common and debilitating neurodegenerative disorder that primarily affects older adults. It's characterized by the progressive loss of dopaminergic neurons in a part of the brain called the substantia nigra. This leads to symptoms like tremors, stiffness, and difficulty with movement. Currently, it's estimated that by 2040, around 14 million people worldwide will be living with this condition. Now, one of the key players in Parkinson's disease is a protein called alpha-synuclein. In healthy brains, this protein has a normal function, but in Parkinson's, it misfolds and accumulates, forming toxic aggregates. This accumulation is thought to contribute to the death of neurons, leading to the symptoms we see in patients. Despite extensive research, we still have many unanswered questions about how alpha-synuclein causes toxicity. There are debates about how it spreads from cell to cell and what exactly triggers cell death. One major challenge in developing treatments is the lack of reliable biomarkers. These are measurable indicators that could help us understand the disease better and track its progression. Now, let's shift gears and talk about PARP inhibitors. PARP stands for poly-adenosine 5-diphosphate ribose polymerase, which is an enzyme that plays a crucial role in repairing DNA damage in our cells. When DNA gets damaged, PARP helps fix it by adding PAR units to proteins, a process called poly-A-depuribosylation. Recent studies, including one by Cam and colleagues, have uncovered a new role for PARP1 in the context of alpha-synuclein toxicity. They found that when alpha-synuclein fibrils are introduced into the brain, they can cause DNA damage through a process involving nitric oxide. This damage activates PARP1, leading to increased levels of PAR, which then interacts with alpha-synuclein, accelerating its toxicity. This creates a feed-forward loop. More alpha-synuclein leads to more DNA damage, which activates more PARP1, resulting in even more alpha-synuclein toxicity. It's a vicious cycle, and understanding this mechanism opens up new avenues for treatment. So, how do PARP inhibitors come into play? Since we already have PARP inhibitors approved for certain cancers, researchers are looking at them as a potential treatment for Parkinson's disease. By blocking PARP1, these inhibitors could reduce the levels of PAR, thereby decreasing alpha-synuclein toxicity and potentially slowing the progression of the disease. Additionally, researchers have found higher levels of PAR in the cerebrospinal fluid of Parkinson's patients compared to healthy individuals. This raises the exciting possibility of using PAR as a biomarker for the disease, which could help in diagnosis and monitoring treatment efficacy. While the findings are promising, there's still much work to be done. Future research needs to validate PAR as a biomarker and assess the long-term safety of PARP inhibitors in patients with progressive neurodegenerative diseases. In conclusion, the intersection of basic research and clinical application is crucial in the fight against Parkinson's disease. The work being done on PARP inhibitors not only sheds light on the mechanisms of alpha-synuclein toxicity but also holds promise for new therapeutic strategies. Thanks for joining us today. If you found this video informative, don't forget to like, subscribe, and hit that notification bell for more updates on the latest in medical research. Let us know your thoughts in the comments below. Until next time, stay curious.
PARP